All right, thank you for tuning in. Today I'm going to give a little demo on how to run basic data analysis using Catalight. So to start with, we'll go to a repository for Catalight that I already have installed onto this computer. So here I have this Catalight repository that you can clone from the GitHub page. And if you go into this repository, this folder, you'll see that we have a subfolder in here called example data. So this is the data that we're going to work with today. You can see that there's some demo samples and a calibration file. We'll go ahead and open up both of these. So here is what the demo calibration file looks like. It's just got 3 molecules in it, a couple of slopes and their intercept and some elution times. And this matches with what chemicals are going to be found in the data that we have to work with in these example data sets. So the example data sets, like I said, there's 2 samples. And inside of each of these are a couple of different types of experiments. So there's flow sweeps and power sweeps and temperature sweeps. We'll go to one of these. And then inside of this is the standard kind of data layout that you get with any experiment you run inside of Catalight. Inside of the data folder is going to be a bunch of different experimental conditions for whatever independent variable you have for this type of experiment. And if you click inside of either of those, you're going to have the output of the gas chromatograph. And most importantly, you'll have these ASCII files. And that's the data that we're going to be looking at anytime we run analysis inside of Catalight. Then inside this results tab, you can see that there's nothing in here yet. So if you run an experiment with Catalight, this is what is going to happen right after that experiment is run. You're going to have a bunch of data that gets put out by the GC in this organized format. Everything is structured identically. But inside your results folder, you won't have anything here, any plots, any ppm conversions. And that's what we're going to do in this tutorial. So we can open up the run initial analysis Python module. You don't have to open this in an IDE. You could also run this from the command line. You could also write your own script to access this by calling this main function. Today we're just going to have it open inside of an IDE and we're just going to hit run on it to run the file. When you hit run, or if you call it from command line, it's going to call this if name equals main script down here at the bottom. And this just prompts you to get user inputs with this function. And then it calls the main script. So you could write literally this exact same thing in your own script and import in this module. Or you could provide all of these input components or on your own through scripting. Just type it into a file and then enter them into this name function. But today we're just going to work with the UI. So to do that, and one of the easiest ways to run any of these files like noted with this run demarcation is to hit run on the file. You'll see command interface open up in the background. Then it'll open you up to your file dialog. For the calibration file selection, which is the first thing that most of these different run Python modules will ask you for, it's just your basic systems file dialog. So we want to go look at that example data set. So we'll go to our Catalight repository. Then we'll go into the example data folder and we'll select this demo calibration. So if you had run this on your own machine and you already have your own calibration file that you've already analyzed your calibration data, and you can see our other video on how to do that, then you would want to hit that, click that calibration file instead. But if this is your first time using it, you might want to start out with just using this demo data to make sure that you get, what's going to happen before you get started. So we'll open that up, and that just gives the path to wherever that is. And now we have both of these two demo sets. So there's kind of two ways that you can select this data. And you'll see that this also comes up in this Qt non-native file dialog. So it looks different, mostly worse than the other one. But what this enables is a cool feature that you can't get with the native file dialog. So if we back out here, if we were to click on the example data folder, we could return out all the different folders that contain data, or the experiment folders from within this folder. But if we go inside of it, we can also select multiple directories. So you can hit Control and click, and you can see that all of these directories pop up at the bottom in a list. And when there's just two, it really doesn't make a difference, right? But say you have a folder that has all of your ensemble catalysis results, and you might have 20 different samples that you've analyzed. Or say in one sample, like if we go into here, you have multiple different experiments. Well, you can come and you can select which ones you want to look at specifically, and select any subset of it that you want to. Here, I'm going to select both of them, and I'll just do it with this Control click again, and we'll hit Choose. And now it opens up this plotting instructions UI. So for all of these modules that start with run and underscore, there's this built-in kind of simple UI that lets you enter in all the inputs that you normally would if you were running the main script through some kind of scripting interface. This is just to make it a little bit easier, especially for some users who might not be as familiar with Python, or if you don't want to write new code every time that you're trying to run some basic analysis. So this is just some simple entries to make into all of these. Make sure when you enter these top three, these strings should match exactly with what's in your calibration file, including the capitalization. So your reactant is the chemical ID that you put into your calibration file. Make sure the capitalization matches. So here, actually, my last calibration file is uppercase, but this one's actually lowercase in the demo data. So we'll put lowercase c's and h's. The mole balance element, it actually shouldn't be case sensitive, but we'll go ahead and we'll just put lowercase c anyway. Figure size, you can select whichever one of these that you want. Usually when I run the initial analysis, I like to use this 4.35 value because you can put a nice 3-figure across PowerPoint slide with those. And then the time to units, I usually set this as the default to 2. And usually I leave everything else as true. You want to save the data. There's nothing to overwrite in this case anyway. And then I usually like to add the baseline correction. So now we can hit OK on this, and you'll see that it begins to sweep through all the different experiments that we have within those main directories, and it's going to run the basic analysis for each of those. And occasionally you can also notice that we print out these little warning messages saying that there's other peaks that are detected. So that comes out anytime that the peak finding software is finding more peaks than what you have inside of your calibration file. So some things that are showing up outside of the elution times that you put in, the peak finder is detecting those things, and it's basically saying, hey, what you might want to pay attention to what this is. It doesn't do anything more than that. So if you want to look at those, then you need to go and you need to pull up those specific runs and see what those other peaks are, and try to figure out what's going on in your chemistry. So now we'll come back here to this demo data set, and we'll go into any one of these different experiments, and you'll see now in the results log, we've populated this entire thing with data. So this is actually a different results log that I ran previously. This one is the one that we just ran. So I ran this other one twice. This one is the one that we just ran. So you can see the 4.35 width, and I put this prepended string for the figure width, just so that if you want to have multiple different sizes for all of these different figures, you can have that each time you run it. If you want to run it again to get the 6.5 wide one, then you can have the exact same data just in different sizes. So inside of here is 3 different plots. You can see more information about these plots in the documentation, but you can go ahead and you can click on any of these. They're all saved as SVGs, so working with some kind of free vector editing software like Inkscape is really helpful if you want to quickly browse through these SVG files. They're saved that way because they're really nice and easy to edit after, versus like a PNG is a little bit harder to work with, and also doesn't scale as nicely as a SVG. And then inside of here, there's also these 2 different files, the average concentrations and the standard deviations in the concentrations, both as CSV files. So with either of those, you can just go ahead and you can open them up. They'll come up in a nice PowerPoint format, and you can see the different molecules, the different ppm concentration values that you get, as well as the temperatures for each of the different run conditions. And you also have this NumPy file of concentrations. And this is going to be a 3-dimensional NumPy array. So it's kind of hard to find a good native format to save that in. So we just save it as a NumPy array. When you import that, that contains the ppm concentration and the timestamp for every single molecule, for every single run number, if you run duplicate runs, for every single condition for your experiment. So basically, anywheres where you have one of these ASCII files, you have a NumPy array for every single one of these, which gives you a 3-dimensional data set. So the last thing that we want to talk about before we end this session is we want to look at these composition sweeps, because this data is going to be a little bit different than the rest. So we'll go into this results and we'll pull up one of these. Not this one. We'll pull up one of these. So the one thing that I want to point out is that composition sweeps, these can be a little bit of a messy thing to plot. So when you run a composition sweep, there's a lot of different types of experiments that any particular user might have in mind, right? You might want to do a composition sweep where you're varying, say in this case, the ratio of acetylene to hydrogen, or some reactant to some other reactant. So you might want to run a 1-to-1 ratio, a 1-to-2 ratio, a 1-to-5 ratio, a 1-to-10 ratio, and so on. But you also might want to keep that ratio the same and just vary the partial pressure of your reactants relative to some inert gas, right? So you might keep a 1-to-2 ratio, but you might want to do 1% reactants, 2% reactants, 5% reactants, and so on. So there's not a great robust way to keep the interface simple, but still allow the user that kind of flexibility. So in these composition sweeps, the x-axis data, this is actually not plotted in any number of units. This is just plotted as the condition number, right? So this is always going to come up as this linear spacing. And you see that the x-axis looks terrible here. And that's because this is just a bunch of strings that's getting put out. So this is showing you the string composition. So literally, if you go into your data sets and you look at your folders, it's taking this string that defines each one of these data folders, and it's just plotting that out. So anytime that you want to do a composition sweep, you need to be aware that this data on the x-axis is not really what you're trying to vary. And I've written a different tool to convert the x-axis on all of this data after the fact in post-processing. So it's a little bit extra work for you to actually plot out and analyze the data at the end of it. But that's just done so that we can keep this as flexible as possible. for any type of experiment you might want to run in terms of a composition suite.